Hello, you all. Thank you for coming for this talk about microservices. I'm Nelson Gomes. I work for BitSide Technologies, and today I'm going to do a step-by-step on how to create microservices easily and reliably. I'm going to introduce Swagger for those who don't know it, some of the existent Swagger tools, and talk about how to scale. First of all, some people tend to confuse a REST API with a microservice. They are not the same thing. Usually, REST API is used to build microservices. But we'll talk about that further. Our talk today is going to have 3 stages. First is to set up the server. The second is how to create a REST API for using Swagger. And the third topic is how to distribute it and scale it. First of all, microservice introduction. Some people, as I said before, tend to confuse both microservices and REST APIs. Microservices use REST APIs to do its core, but a microservice is a little more. So we use a microservice architecture to extend and scale REST APIs in larger systems. Usual REST API has the usual CRUD operations to create, get, create, read, update, and delete stuff, but usually a REST API is stateless, cacheable, and a layered system when you use a microservice. Just a minor introduction how a REST API should work. The response codes for a REST API depend on the success of the operation. Here is a small workflow on how to give a response code according to the status of the operation. You can find a lot of best practices on the web. I give you a short link on how to define your response codes through your APIs. But microservices are more scalable. You can have usually a REST API only has a server. A microservice can have hundreds of servers. Each server can supply one or more services, and you can scale each service of your microservice according to its needs. So you can have basically one box to serve one service, but you have, for instance, you have a login service, you can have 1, 2, 3 machines, but if you have a lot of operations to get users, to get some stuff that is called thousands of times per second, you can have more small instances of each REST API to provide the service. So instead of having one computer providing all stuff, you can have a lot of computers, each one providing a different service or common services if you need to scale. Usually on microservices architecture, you can map REST API paths to services using an Nginx or hardware load balancer. So, for instance, on a login service, you can have 3 machines, but you can have 5, 10, 20 machines supplying the needs of that service. That makes very easy to extend your scalability because if you have an API that is called 10 times a second versus an API that is called 10,000 times a second, you can have one machine or two just to provide an API, but you can have a pool of servers, 10, 20, providing the API that is called more. So you can scale very easily. What is the main disadvantages of using microservices? They are very, very complex. You need to have load balancers, you need to have the monitoring, you need to handle errors and downtimes. You can have issues with versioning. You can have several versions of your API being used at the same time. And sometimes it's hard because sometimes you have microservices that consume other microservices. So you have a cascading effect. You have a layered system of microservices that depend on each other. So a user microservice can call another microservice that gives all users or gives all the information about that user. So it's not a single microservice system. You can have several APIs calling each other, and that makes, for instance, very complex to make a transaction on a microservice. If you have an operation that calls 3 microservices and you need a transaction, you will have a problem because everyone knows that HTTP doesn't cope very well with transactions when you call several HTTP requests and one fails. So how do we reverse the failed transaction on a web system? Let me show how the easy steps on setting up a Jerry Jersey server. To start, we'll create a Java project with a WAR packaging. We'll have a few dependencies as usual. I will provide at the end of this talk the links, the link to the project that is used as an example for today's talk. So, in special, I'm using today Jerry. Jerry has at least 2 ways of startup. So you can package your application, build a WAR file, and deploy it with on a command line with the Jerry commands. As you can see below, Jetty jar and Jetty runner. The Jetty runner is the jar that implements the Jetty server. And you can pass on your application. But in today's presentation, I'm not using this command line. I'm using a standard Java main. So I can run the application from my IDE, from Eclipse, for instance, and test everything without needing to deploy anything to an application container or something like that. So this is a very simple main example to start a Jenny server on port 8080. So with this, you are ready to run a simple web application. You define your path to your application. You do a Jetty start, and you're ready to go. So after do this, you can go to your browser and access to your local host on port 8080, and you have an empty application on Jetty. So the next step will be to declare your web app. So you will need to create a web XML file declaring your packages for your application. So you'll see that the COM SF FW API version 1 and 2 are being declared to the application. I've done a very simple ping test that returns a string on that package. So doing the same access to the APIs, we'll have a response from my web service. So now I can call API v1 ping and receive a ping, and go to API v2 ping and receive a pong2. This way I can have 2 versions of my API being used on the same server. For database access, there is a lot of frameworks on Java for database access. I mentioned a few. For today's presentation, I will use two frameworks I like a lot. Especially, I'm using dbutils and Hickory CP. dbutils is a very raw framework to access a database, but it's very reliable. So when you use very complex or you customize your own JDBC layer, sometimes you have a lot of problems with resource management. You'll tend to have problems like out of memories because you don't clean up all your resources. And sometimes your application will run for a day or two, and after a week it will crash because you have some issues on it. With the dbutils, because dbutils is very reliable, it doesn't have that kind of issues. It manages its resources very well. It's very reliable, very stable. If your application goes down and goes up, for instance, if MySQL server goes down or Postgres goes down, dbutils will continue just if you handle your exceptions correctly. So your application will resume as soon as your database is up. That's very important to have a reliable layer on your system. dbutils with Hickory CP will basically, it's a database layer with a connection pool layer. Hickory is known to be very fast on connection pool management. It's one of the fastest on the internet, beats all the frameworks, including the one I used previously, like DBCP, Apache Commons the database pool. So these two together give you a very fast database layer and a very fast connection pool layer. To do web services reliably, usually you need a very good caching system. People tend to use database for everything. You should have a midterm where caching will be used as much as possible to avoid a query to the database. Each query to the database takes time. If you want to do fast web services, you must cache as much as you can to make your application faster. Of course, caching has another issue and advantage. Usually, if your database goes down, probably your cache will have the data and hide some issues with the database, but it helps to decrease the load on a database and on other systems. So if the caching, even for a minute, is possible, try to use it as much as possible. On caching, you can do at least two ways. You can do a reactive cache. When you receive the need for a key of a cache, you can try to generate it and store it. Or you can do a proactive caching. If you know your set, generate and heat up your cache system. So when you have a hit on the cache, it will have all the keys it needs to work fast. There is also a midterm where you can have a cache that regenerates itself in some time period, every minute or so, or every hour or so, depending on your requirements. But this way, you will have very ready-to-run information on your application. Of course, in caching, you can have several levels of cache. You can cache the response. You can cache your date. You can cache your database query. You can cache all kinds of stuff. But that depends on the needs you want. Probably on web services, sometimes it's useful just to cache the response. You have a response object that you pass on. If you receive the same parameters, you can give the same response and avoid going to the database, going to other systems and making your application very fast. Caching frameworks, you have a lot these days. You can the one that is most used in Java, you probably is Caffeine or Guava Cache. But caffeine is very fast. It's in process. But you have a lot of different caching systems today, especially the distributed ones that provide reliability. So if one of your nodes goes down, you will have a distributed cache that will maintain your caching. So you will not see failures and you will have data available. Of course, when you use a distributed cache, probably you will have some latency to go to the network to fetch your information. A good idea is to combine both. So if you have a local cache and you have a distributed cache, you can try to store locally the items that you use more frequently to avoid going to your distributed cache. This way, you have reliability and we have performance. So this is a small example on how to use Caffeine. Caffeine is a framework for caching in Java. It's very similar in a way, the way it works, but it's faster than Google Guava Cache. So you can even replace your Guava caches with the same API on Caffeine. On these examples, you will have, for instance, on the first one, you can have you can pass on a function that knows how to generate your data, but you configure your caching system to drop the keys after 5 minutes if not being used, and you can configure it to regenerate your cache every minute or so to avoid having stale data on memory. This way, you will have your cache always warm before hitting the caching system. Below, you'll see a default caching example that is try to find the key on the cache, doesn't find it, generates it, and stores it. That is the old way of doing things, but the top example is very, it's better because it will keep your cache warm and avoid misses that cost time on your application. So one of the big points on this presentation is Swagger. What is Swagger? Swagger is a specification, is a standard. So when you define a Swagger, you are defining your APIs. Usually, some people say, I need to generate my Swagger definition and create my server and my client with it. I tend not to use it because it's not very easy to maintain your application, especially because usually at the beginning, no one knows how your application will be defined and the APIs it will need. So if you generate your Swagger file, you will have to diff your code every time you regenerate your server, and of course, you will have some issues maintaining your application. And of course, you don't know the code that is generated. So today we will talk about the 3 different tools that used together will help a lot. The Swagger file generation. So we'll annotate the code in Java with the Swagger annotations. This will be plugged into the Maven. So every time I do a Maven package, I will have my Swagger file regenerated, my documentation generated, so I don't have to generate my Swagger file by hand. It's not very friendly. The Swagger UI, it's a very helpful tool that we'll see in the demo. Allows you to use your Swagger file definition to call your own APIs and test them very easily. And the Swagger editor that you can use to generate your client stubs based on the Swagger file. So the main issue for me on not using the Swagger file to generate my codes are basically two reasons. If my API changes and I have a lot of code filled in on my server-generated codes, every time I add a new method or change a new method, I have to diff my codes and compare it to the new code generated from YAML file. That's not very friendly. It can give you a lot of conflicts, problems, issues. And the other reason is I don't know what server and how the server is implemented. So if I use a code generator, I will have a server that probably is not what I want or what I need or not the technology I want. So the annotation for me is a very more feasible way to generate Swagger files and keep up my code. And I can easily change from Jetty to other server technology. I don't have any issues with it. So, talking about annotations in Java, basically, if I annotate a class with API, for instance, I will declare to Swagger that that class is going to be part of my Swagger file. So I can declare it, give it some information, and then I can easily add annotations to my APIs, declare what the method does, declare my responses codes, what happens when a response code is successful, what returns in case of success, the response class. So for instance, in this example, I will have a ping method that calls, returns a string, gives a 200 codes and a successful operation, and returns a type of string class. So this is a very simple example, but works very easily. For more complex structures, I can declare response container types. I can say that my output will be a list of objects, sets or maps, and I can declare the class of my objects. So in this case, I will return, on this example, a list of book class objects. So I will receive a list of JSON with all my books ready to use. Further going on the annotations, we can also declare parameters. So in this case, I will say that my API param books will have a list of books that is a required parameter, and a comment string that comes from a query param from my URL. But I can change the type of my query parameter to a post parameter, to a path parameter. So this way I can receive data from basically every web source that can give information to my application. Further on, I will declare on my class books the types, the information about the types. For instance, the book ID, it's an integer, but that is done automatically by reflection. So I only declare the value, say if it is required or not, and give it an example. So with these simple annotations, I can basically generate my own Swagger file. Doing a Maven package will produce the documentation of my project. We'll generate my Swagger file with all the definitions and the information about the APIs, the methods, the parameters, what are required, what is not required. So basically, I'm ready to go and give it a try. So let's set up the Swagger file generation. I hooked up my Swagger generation to the package stage of Maven. So every time I do a package, I will have my documentation and my API refreshed. So if I change the method, add the parameter, change some annotation or add some method, everything will be generated on the fly. Every time I compile it, it will be generated. So this is a very simple way of keeping my API consistent. Because if I have 10 branches every branch with a single and different version. I don't have any issues with it. I can have them. Each one has its own version, but the content will be produced every time I do a package to deploy that version. So I don't have any issues on updating my server and eventually my clients. How to prepare your Maven file? We have to add a plugin to the Maven, basically declaring the Swagger plugin. So I will give the schemes, HTTP or others, my template to generate the documentation, that it's a template system that generates the output. And I declare the packages for it to scan. So it will scan the package API v1 and produce the output. So if we go further and do the Maven package and start the main, basically we'll have already documentation being generated, an empty stub, of course, because I didn't add that much. But I will have my information. I will have my Swagger file in JSON or in YAML. So, next step. Now we have our Swagger system producing output. Now let's set up the Swagger UI. What is the Swagger UI? A Swagger UI is a set of static files that use the YAML to generate, using JavaScript, your a simple interface for you to test. So if you change the URL on the Swagger UI to point to your YAML file, you will have generated on-the-fly web page with all your methods, examples on how to use them, and then we'll see this as an example at the end. So you can call a post, a get, a delete on your user interface without needing to build code to test your methods. So you can, in 5 seconds, create a book, as we will see, very easily. This allows you to test everything, to interact with your APIs without the need of making a client by hand to test it. It's very useful. So, client generation. One of the biggest advantages of using Swagger is the Swagger editor. The Swagger editor, it's online, it's a web page, but you can hook it to your Maven or your code generation. So you can generate stubs based on your Swagger file on basically every language existent. So if you have a Swagger file, you can even generate your server on several languages on the left, and you can generate clients on even more languages based just on your definition. So if I create a microservice project using Swagger, I can generate stubs for and clients for at least about 20, 30 languages. And if you don't have your own, you can extend it and generate your generator for your own language or for your platform. Just a side note on Jackson behavior control, because Jackson is the framework that decodes your JSON and converts it to objects. But one of the Jackson behaviors that needs to be changed by default is when I do a post that is empty. If I do an empty post, it will tend to give you a 500 error without even calling your method. Why? Because Jackson is configured by default to throw an exception if an empty post is given. You want a post with a JSON, it tries to parse it, doesn't have any content, throws an exception, doesn't call even your method. This change on behavior allows you to receive a null object on your method, catch the exception, throw a decent error, and log information that someone is calling your method with an empty body. So, circuit breakers. Circuit breakers are one of the most important features on microservices. Why? because microservices tend to scale to tens, hundreds of servers, and sometimes, and it happens more than probably someone think, you have microservices that call other microservices. Each microservice depends on some resource, a database, a file system, other systems. And when the system goes down, usually your application tends to stall waiting for it. So if you have a database that is down and you have 5 requests per second, you will see that those 5 requests per second will be blocked. So every second that it passes, you will have 5 threads blocked, 10 threads blocked, 15 threads blocked. And if you have a limited thread pool, that usually is what we have, you will see that in a few minutes, your whole application, your whole microservices infrastructure will be blocked, waiting for a response of a resource that is dead. So the circuit breakers on microservices is a very important feature because it allows you to control the going down movement of your threads. So when some resource is unavailable, the circuit breaking is a feature that allows you to block those requests and avoid the cascading effect of having all your threads blocked. This way, you will avoid crashing your entire system in a few minutes, maintaining it operational at least. So even if some microservice is blocked, you will have your other APIs working and the system will be responsive. Hystrix is an API that you can use to help solve this problem because it prevents and isolates all these errors that can happen on a microservice. So it gives you fallbacks, and you can manage your own state and see, hey, my database is down. I will give you a 500 error and say the resource unavailable and come back later. So this time you won't have your threads waiting 30 seconds, 1 minute to give an exception that the database is down and unblock the threads to receive other requests. One of the major concerns on microservices is statistics. You need to have metrics. You need to know how many errors your distributed system has, how many requests it is receiving. Is it some resources, is it taking too much long than usual? This way you know the health of your distributed system, because a microservice is a distributed system. Today I'm going to talk about Hazelcast. Hazelcast, for those that aren't unaware, is zero configuration clustering system. So I will give a very simple example of Hazelcast at the end. Basically, with a single line of Java code, I can create a cluster and have 5 microservices, 5 applications communicating each other very easily. So if you see at this line of code, the only line of code I have here to set up my Hazelcast instance is the cluster node. So I'm instantiating a cluster node, an Hazelcast instance. So this is all I need to have my cluster working. Hazelcast is a zero configuration cluster, as I said. It broadcasts and discovers all between the nodes, discovers the nodes of the cluster. So I can bring up 5 nodes and they are aware that they exist. It does it by broadcast. So, for instance, if you try to run Hazelcast on AWS, you will need to define the IP addresses on the config because AWS doesn't support broadcast on their network. So this is the only difference on using Hazelcast on AWS. So with this, you can have queues, topics, map reduces on your web server, on your microservices. You can have maps and distributed memory. You can have distributed locks. You can have a lot of stuff that you can find easily on hazelcast.org. You'll see very simple examples, and with this, you can scale. You can even, if you want to create some system of circuit breaking, you can even on Hazelcast use the executors. And for instance, when my database goes down, you can inform all your microservices nodes, calling an executor that executes on all nodes the method created by you that will inform that resource database is down. So execute on all nodes, and it allows you to do that very easily because it's a cluster. So if you call a method on all nodes of your cluster, informing the resource is down, every node will be aware that your resource is down, and this way every node is aware of a state and avoids the calling to a database that is down, for instance. So if your resource is down, don't call it until you receive the information that it's gone back up. Hazelcast also allows you to have distributed memory. So if you have a very big set of data, you can easily have all the nodes' memory working for you. So instead of having 100 megabytes of cache on one node, you can have 1 terabyte of cache distributed on 100 nodes. With this, you can basically extend the caching depending on the size of your application and your data, of course. So, microservices are very useful, but they have a problem. They have a lot of problems. They need to be very well implemented. People try sometimes to do everything online. If you can do something offline, do it. Because users don't want to be waiting for some response. So if you just can validate your request and store it on a queue that will process it afterwards, just store it, give an OK response, and your microservice will be very fast, and your users will be very happy. If the operation is very complex, you can parallelize it somehow on your nodes, or if it is very complex, you can put it on a cluster like Hazelcast and shard your loads between all nodes of your cluster. You should cache everything, or as much as you can. Even if you do a 1-minute cache of something, that avoids a query or per request. Probably if you have 100 requests, you will avoid 100 queries to your database. So you will decrease your database load, you will increase your application performance. It's a win-win situation. On microservices, it's a very good practice to avoid multi-request transactions. So if you have a transaction that needs to do transactions on three different systems, try to avoid it, because it's very complex to go back on the failed transactions. You need to have mechanisms to revert your failed transactions. If you have a lot of data that you provide, you should and must provide paging on your APIs. So if I have one database with 1 million requests, and if a user calls get all records, you will probably spend 5 minutes downloading data for that customer and make the web service unavailable, load your bandwidth, make it very slow, stalling your database. So Every API that provides information, and a lot of information, should have some sort of paging mechanism on the results. So you will ask for the first page, second page, third page, but every time you ask it, it's a very small set of data. You won't stress your database and your bandwidth on a single request. And of course, it's easier to parse 1 megabyte of data than to parse 200 megabytes of data on a single download. Finally, you should Dockerize it. I'm not sure how many of you use Docker. I hope a lot. But usually Docker is a very simple way to scale. You have a lot of systems that allow you to scale. You can use the Kubernetes to have your image spread for tens or hundreds of nodes. You have Docker Swarm, Amazon ECS. So basically, if you provide an image of your container to one of these tools, you are basically a small step of making it a larger system, because with this, you can very easily increase your system and manage. And of course, if you have different APIs, you can, in some systems, configure the system that for if my load goes up, then X%, deploy another instance, and scale as much as it needs automatically. So at 8 a.m., for instance, you probably will need a node to provide your methods. But when people try wake up in the morning and go to the internet, you will see the load increasing, and as the load increases, you can deploy and increase more nodes and reduce basically the load on the nodes existent. So with Docker, I'm not sure if many of you use it. You can, for instance, if you need to try a specific Ubuntu Debian version or other version of other system, you can just do a Docker pull to download your image, and just Docker run your image and open a shell. If you do this, you will have Ubuntu image running on your laptop in less than a second. The Docker pull usually is heavy. You have to download a lot of stuff. It takes a while. But after that is done and the image is on your laptop, you can start a Debian, any system, basically, on a second. Just, if you try these commands on your laptop, you will run the Docker run and have a shell in a second. So, now we're going to see some stuff, some neat stuff, I hope. See the demo working. So let me change it. So, let me grab it. So I'm loading up my application. Where is my window? Let me change this. Okay. So this, if I go to my local port 8080, I will have my Swagger UI. This is a set of static files. So as you can see here, you have an example of the Swagger UI downloaded from the internet that has a list of operations that you can call very easily. But usually you have to edit your Swagger UI to point it to your local machine. So let's point to our local machine, to our Swagger definition. So this content was generated with the annotations I put on my methods. So I have these methods. It's very easy. If you go to swagger.json, you'll see the Swagger file that was generated. If you go to Swagger YAML, you see the same version, but on YAML style. So this is your definition. But this Swagger UI gives you a very useful tool, because besides doing the method, I didn't do any client. So I need to test my API. So if I want to test my ping method, I just go here, expand information. This is all done using annotations. Give it a try. It's doing the first request, so it takes so long. And I see the curl option if I want to use it on a command line, the method, the URL that was called, the response body, the response code, and the response headers. So I didn't do squat, but I have a working client to test all my APIs. So my second attempt will be faster because it's already loaded, so it's very fast. I done also another interesting stuff. As I told you, I created a Hazelcast instance, so my node is working on cluster modes. So every time I call a ping, I'm incrementing a counter that is cluster-wide. So if I want to count all the requests on my cluster of hosts, I'm incrementing an atomic distributed counter. So if I go back to my environment, I will go and start another instance of my server on port 8081. So now I have two servers, the Jelly servers, running on two different ports. So if I point it to my Swagger file locally, 8081, I have two servers working on two ports. And I will do a ping just to initialize my system. But because I'm using Hazelcast as a cluster, if I check the counter of requests on my cluster, I will see that I have already 7 requests done, but on 2 different nodes. Now I have 2 servers working on 2 ports connected by a clustering system, and I can do everything I want. I can ask them to do stuff. I can have a map. Basically, I have an infrastructure to communicate with all my nodes, to be aware of my nodes, to scale up to 10, 20, 50 nodes very easily with 1 line of code. So going back to the initial example, for instance, to get all my books, this is an example. You can see the model that was generated automatically by the annotations. I have my model. I have an example. I want to fetch all my books that are in the database, and these are my books. I will show you the code. To create books, it's even easier than that, because I created a method. I have an example that is built by the information on the annotations. I just need to click. I already have my JSON objects. I can even add more records to my JSON very easily. Do a book title 3, a book title 4, add a comment, some sort of comment, and post it. So it says that it stored 2 records of books, created 2 books, and I have my content already stored into the database. So if I update my books list, now I will have the item 6 and item 7 already created. So very easily, I could create a very simple API, declare it, test it with a few lines of code. And I have a cluster connecting all my nodes, so I can scale very easily and have states, information, distributed information, queues, topics, and all of that is needed. But the interesting stuff on the code that I used for this demo is that if I go to my get books example, if you can see it, I'm incrementing my counter. It's a cluster-wide counter. And I'm creating a data source. This is the DBUtils and Hickory CP. So basically, I created a connection pool and created an object to do a query. So my entire method to get books, serialize, and give a response, basically, it's a one-liner. So on this one-liner, I'm creating a response with 200 codes, using a Jackson mapper to generate the JSON, using the runner to query all books, and using a bin list handler to serialize the output of the query. So with one-liner, I did a method that generates a list of books. The same thing for the create books. It's very simple. If you see the codes, I created a database instance, inserted all books, and gave a response if everything went OK. So I did a very simple API with a few lines of code. I'm able to scale my cluster. And if you want, you can use, for instance, services like the ones that allowed you to register your services to increase automatically. So every time you deploy a new node, you will inform a system, hey, you have another node providing service X. So your load balancers can reload automatically the configuration, add a new node to the load balancing system, and scale. So to finish up, I think this is a very simple example that show how to create microservices. If you have any questions, any doubts, you can have the source code available on GitHub. So if you want to give it a try, you just create a database, configure the password, and you'll have a minimal system to start working with Jetty, create microservices, and basically scale. Questions and answers. So, thank you all for coming. I hope you have learned something.